Hello and good day, folks. Here with you to go over Algebra packet number 8. Note the due date, March 9th. That's the last week of the trimester. So not only this packet, but packets 5, 6, and 7 that you may not have turned in yet. All those need to be turned in this week for points. So let's begin. We've got two planes that depart from the same airport at the same time going in opposite directions. One of the planes travels 60 miles per hour faster than the other one, and they are 1,820 miles apart after 2 hours. How fast is each plane traveling? So especially in algebra, if you're unsure how to start something, your two options I highly recommend are to either draw a picture or look for an equation. And for this one, we're actually going to do both. Okay, we're going to start by drawing a picture. Here's our airport, and we'll call first plane A. Goes out, and we're going to kind of break this down into 1 hour sections. Okay, after 1 hour, plane A travels that far. After 1 hour, plane B travels this far. And you'll notice that I made plane B's line a little bit longer than plane A because plane B goes further. It's traveling 60 miles per hour faster. So after 1 hour, it's going to have gone further than plane A. And so what we want to do here is we want to identify or assign labels. You know, what are we going to use to represent how far plane A went and how far plane B went? Well, if we say that plane A went X distance and plane B is going 60 miles per hour faster, we can assign that same distance plus 60 more to plane B. And the reason why we can kind of mix miles per hour and distance here is that because we are talking in terms of hours and miles per hour, that however fast they're going, that's how far they went, because our units are all in hours here. Okay, so X for plane A, plane B goes 60 miles per hour faster, 60 miles that speed, so X plus 60. After the second hour, let's extend this out. Okay, that first to second hour, again, plane A is going to go a distance of X. So total, after 2 hours, plane A has gone a distance of 2X. Plane B, after 2 hours, has gone another X plus 60. So here's our picture, and the number we haven't used yet, this 1,820, that represents the total distance that now separates plane A and plane B, right? They are 1,820 miles apart. So the equation we can set up is saying, well, what makes up that 1,820? Well, we have X plus 60 plus another X plus 60, both coming from plane B, and then plus X and plus X from plane A, and total that equals 1,820. So solving this equation here for X, essentially where we're headed, okay, solving that equation for X isn't our final answer, but we use that value for X to get the speed of plane A and the speed of plane B. For plane A, it is just going to be X, and for plane B, it's going to be that plus 60. Okay, but this is kind of how you want to start. We drew the picture, we made the equation, and now we can solve for X. If you found another way to do it, great. Just write that down. Make sure you show your work, and that'll be fine. The next one, Mrs. Johnson likes cookies. Each student in her 8th grade class gave her a cookie. A third of the students each gave her an oatmeal cookie. A sixth each gave her a cinnamon cookie, and a fourth of the students each gave her a chocolate chip cookie, and the remaining 9 students each gave her a peanut butter cookie. So what we talked about in class here is that of the 4 values that were kind of given, 3 of them are fractions, whereas 1 of them is an actual quantity of students, actually talking about 9 students. So the approach that we took here was we want to write this 9 in fraction form. Because if we know that 9 represents, say, half the class, we can answer the ultimate question, which is how many students are in Mrs. Johnson's class. If we know that that 9 represents, a 1/10 of the class, then we can get to that whole of how many students are in the class that way too. So what we did was we said, well, let's see how close are we to a whole. 1/3 plus 1/6 plus 1/4. Okay, how close are we to a whole? And we added these together, and we got 9/12 as a total, which means that we still need 3/12, right? 9/12 plus 3/12, that's what we need to get to one whole, get to the whole class. So that means that these 9 students represent 3/12 of the class. And there are a couple different ways you go from here. You might try simplifying fractions, or just kind of drawing it out perhaps. But essentially, if 9 students represents 3/12 of the class, how many students are in the entire class? Next one is the 5-card challenge. Not much explanation here, I don't think. You're going for 18 points. At least one of your equations needs to use all 5 cards. Do use a calculator to check your answers, though. Your calculator always does the correct order of operations. So when you write something down on the paper, if you miss a parenthesis, or you don't put the parentheses in and you should, or you don't put it down correctly, if you type that exact thing in your calculator, you can tell whether it'll catch that mistake for you. You can tell whether you are right or your equation is wrong. So use that tool. Next one, identify if the expressions that are equivalent to the given one, defend your decision. So the given expression here, 12x plus 27 divided by 3. And your job is to tell me whether or not each of the 5 expressions is equivalent to that or not. So what you might want to look for here is, what's different between one equation or one expression to the next. For example, you might notice that in this one, 24x plus 54 divided by 6, that if you multiply 12x by 2, you get 24. If you multiply 27 by 2, you get 54. If you multiply 3 by 2, you get 6. Okay? And like we've seen in systems of equations with elimination, if you multiply or divide everything in an expression by the same thing, it's going to be equivalent. One way we can prove this, or another method you could use for other ones on this page, is pick a value for x and plug it in. Let's take 2. If we take 2 and we plug it into 12 times 2 plus 27 divided by 3, well, 12 times 2 is 24, plus 27 is 51, divided by 3 is 17. If we plug in 2 to this expression, 24 times 2 plus 54, and divide that by 6, we will again get 17. And because we plugged the same number into each expression and got the same result, in this case 17, we know that they are equivalent expressions. And I just picked 2 off the top of my head. I picked 2 because it was relatively small. It's easy to work with. You could pick 5. I think in class we picked 9 or something like that. Okay, but that is another method that you can use to determine whether or not these expressions are equivalent. Pick a value, plug it in, see if you get the same result, or look for connections. Hey, I doubled 12, I doubled 27, I doubled 3, I got 24, 54, and 6. These are the same. Okay. Make sure you are defending your decision. Show me the work. Write out your explanation. Just tell me, yes, these are equivalent because, or no, they are not equivalent because. Next up, we have the area of the shaded region. And in this case, we have triangle ABCD and PQRS. And we know that POS is a semicircle. And so in class, we noted that the area of the entire figure, which is really just square ABCD, is 100 because we have 10 across the top. It's a square, so it's 10 down the side as well for an area of 100. And in the spirit of Christmas, this makes your final answer, that percentage here, a lot easier to calculate because percentages are out of 100 anyway. And if your total area is already 100, you'll see that connection when you find the area of the shaded region. So to find the area of the shaded region, we essentially have two separate shapes here. And we talked about a couple different methods we could use to find them. But all of us really kind of decided that we're going to find the area of the semicircle, then the area of this trapezoid here on the left, and then put them together to get the area of the shaded region. Sometimes we find the area of the non-shaded section and subtract it. In this case, we can find the area of the shaded sections directly. So we have a semicircle here with a radius of 4, and we know that because side PQ being 8 and O being the center of the square, then from O to the side PS, that is going to be 4. The area of a circle is pi r squared, and we've come across this before. We don't want the area of the entire circle. We want the area of half of the circle. So we'll be dividing that formula by 2 to get the area of the semicircle there. For this section here, some of us looked at it in terms of a trapezoid, and the area for a trapezoid is 1/2 times the sum of the bases times the height. Or some of us thought, hey, that shaded section there is 1/4 of the area of the outer square's area. So if we look at the outer square, the trapezoid, this section, the shaded area, is 1/4 of that. So we talked about, different methods of finding the area of just that outer square. We said, well, if you take the area of the large square and subtract the area of the smaller square, we'll be left with that outside part. And then we can take 1/4 of that to get the area of this section here. So trapezoid, 1/4 the area of the outer square, either one works, but that is going to, in conjunction then with the semicircle, that's going to give you the areas of that shaded section. Next up, we have our friends in Sweden and their flag. We worked through this took a lot of time, but pretty lengthy and deep dive into the patterns here. So to summarize them, looking at the yellow blocks first, we saw that this is a pretty straightforward, constant pattern of adding 4. To go from one figure to the next, the number of yellow blocks in the figure simply goes up by 4. But some pretty interesting things happened when we looked at total blocks. And this goes back to packet 7. We had a similar pattern to this, just dealing with squares. But obviously in the first figure, there's just one total block there, one yellow one. But then in figure 2, we recognize we have a 3x3 square, which gives us a total of 9 blocks. Then a 5x5 square for 25 total blocks. And then 7x7 square for 49 total blocks. And the pattern that we saw here was that 1 is found by taking 1 squared, 9 is found by taking 3 squared, 25 is found by taking 5 squared, and 49 is found by taking 7 squared. And so we predicted that the next total blocks number entry is 9 squared, which would give us 81. That follows that pattern there. And then we went to the blue ones. And to initially find the number of blue blocks in each figure, simple subtraction, right? 1 total block in figure 1, which is yellow, which means there are no blue blocks in figure 1. Figure 2, 9 total, subtract the 5 yellow, there are 4 blue ones. Figure 3, 25 total, subtract the 9 yellow, there are 16 blue ones. And then 49 minus 13 is 36. And here's where the magic happened, because we recognize these numbers to also be perfect squares. 0 squared gives us 0, 2 squared gives us 4, 4 squared gives us 16, 6 squared gives us 36. And so we would predict that the next one would be 8 squared, or 64. But if you look across and down the table from blue blocks to total blocks, we see we start with 0 squared, then go to 1 squared, then 2 squared, then 3 squared, then 4 squared, then 5 squared, then 6, then 7, then 8, then 9. That pattern is going to continue throughout the rest of the table. Fantastic. Okay? So by recognizing these patterns and looking at what's really going on here, we can simplify our job a lot. And that is the essence of algebra. It seems complicated sometimes, but really we are representing a situation in terms of a pattern, right, to ultimately make things easier for us to predict, calculate, and things like that. So for algebra, your job is to complete the table and then answer the question, how many blue blocks will be in the 10th figure? How many blue blocks in the 10th figure? Next one, we have a cube, and we've talked about 7 shapes in the previous 7 packets, and we found both their surface area and then their volume. So packets 8, 9, 10, 11, 12 are really going to focus on using those concepts in a little bit different light. I give you a cube, tell you it's a cube. I also give you the volume to be 729 cubic feet, okay? And your job is, without any other measurements given here, right? There's nothing written on the cube itself. You need to tell me what the surface area of the cube is and what the sum of its edges is. And so to do that, to do both of them, excuse me, you need to calculate the length of one of its sides. But how do you do that? There's no information given, other than it's a cube and its volume is 729. So we reminded ourselves that the volume of a cube is base times width times height, but more than that, since all sides are the same, it's really just b cubed, or some number times itself times itself. And since we know the volume is 729, we're looking for what number cubed, or times itself equals 729. And we even found that number in class. I believe at least one of the classes did. We determined that it was 9. 9 times 9 times 9 equals 729. Okay? Which means that the side length of this cube, one of them and all of them, is 9. So from there, you can now calculate the surface area of the figure, the area of all of its faces, all of its surfaces added together. There are 6 of them. And then what is the sum of the figure's edges? Okay? So there you have it. Going on to volume here. Here are the magnificent 7, the 7 figures that we worked with, talked about in each of the previous 7 packets. And your job in algebra is to complete 4 of these 7. And the one we did together in class was this first one here. Okay? I give you the volume, 144 cubic units, and this being a rectangular prism, your first job is to write the formula for the volume, which is base times width times height. And from there, you simply need to give me 3 measurements, 1 for the base, 1 for the width, and 1 for the height. That would total a volume of 144. So what we said was that we needed 3 things that multiply to give us 144. And we couldn't really come up with 3 numbers off the top of our head that make 144. So we went a little bit of a roundabout way, which is actually a great method you can use on other shapes in this section. We know that 12 times 12 is 144. And in fact, when you ask most people for 2 numbers that make 144, they'll probably come up with 12 times 12 because it was the very bottom, right square of their multiplication table that they had on their desk in 3rd, 4th, and 5th grade, probably. But anyway, so if 12 times 12 is 144, but we need 3 numbers that multiply to make 144, we can take one of these 12s and write it instead as a factor pair. 3 times 4. Because if 12 times 12 is 144, then 12 times two numbers that also multiply to be 12, 3 and 4, will also be 144. And so there is one possible answer here, 12, 3, and 4. We also broke down that second 12 to be 2 and 6, which is another possible answer. 12 times 2 times 6 will also give us 144. Okay? We also looked at the fact that, if you cut 144 in half, maybe you knew that 2 times 72 equals 144. Well, knowing that 72 can be written as 2 times 8 times 9, that gives us yet a third option. 2, 8, 9 would be possible side lengths of this prism to get us a volume of 144. You only need to write one, but this method can be used in other shapes as well to help you. Okay, so we did this one together in class. I recommend you do that one because it's pretty much the same thing you did on the previous page. But then you get to pick two other ones to do. Okay, if you need help with the formulas, you can look at past packets. You can ask the Google. You can check with your local math teacher or a friend or a parent or whatever. Okay, but 4 of these 7 completed. Then we go on to math exploration and our friend Fibonacci. Okay, your experience with the Fibonacci sequence, I don't know where you're coming in with that. Some of you may have just only heard of it. Some of you may have never heard of it before. Some of you may have used it before. But the Fibonacci sequence is this second row of numbers right here. This top row, the F1, F2, F3 is just the number in the sequence. Like F1 is the first number in the sequence. F2 is the second number. F3 is the third number. The actual sequence itself is that bottom row. And if you'll notice how each number is generated in the sequence, it's generated by taking the sum of the two numbers before it. So 1 plus 1 gives us 2. 1 plus 2 gives us 3. 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, etc., etc. Okay, and this number sequence shows up very frequently in nature, in art, in music, and in mathematics. And we're going to get an introduction to one of those ways today. So it says here, consider long and short syllables in a cadence length of 4. Short syllables are single white blocks and long syllables are double gray blocks. All possible ways of arranging long and short syllables in a cadence length of 4 are shown below. So in the class that I've already specifically talked about this page with, the short and the long cadence thing kind of threw them for a loop, couldn't quite wrap their head around it. So instead, we looked at it as, how can you make a total of 4 using 1s and 2s, where a gray block represents a 2 and a white square, a white block, represents a 1. So this would be 2 plus 2, which makes 4. This would be 1 plus 1 plus 1 plus 1, which is 4. This would be 2 plus 1 plus 1, 1 plus 2 plus 1, and 1 plus 1 plus 2. Okay, just a second. Okay, and so all the different ways using 1s and 2s to make a sum of 4 is what this first kind of chart shows us here. And how many combinations are there? There are 5 combinations total because there are 5 rows here. How many combinations end with a short syllable, or as we made it, a 1? 3 of them did. And how many combinations end with a long syllable, which we kind of explained as being a 2? 2 of them do. And where that combination of numbers, 5, 3, and 2, shows up in Fibonacci, dun, 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 right there. Now you might not be very impressed yet, but just give it some time, okay? And the next one, we have all the possible arrangements for a cadence length of 5, or all the possible ways to sum 5 using 1s and 2s. We start with 1 plus 1 plus 1 plus 1 plus 1. Or we could do 2 2s and a 1. And here's where, if you remember back in packet 3 or 4, something like that, where you had to draw all the different ways to get to the top of Pascal's triangle, and I said the more organized you can make it, the better. You know, there's more than one way to get to 5 with 2 2s and a 1. Your 2 2s can come first, and then your 1 comes afterward, like we have here. Your 1 could come first, followed by your 2 2s, or your 1 could be in the middle with the 2 2s on either side. Okay? When you do this on your own in the 7th one there, you're going to want to make it as organized and as logical as possible. How many ways can you make a 5 with 2 2s and a 1? 3 of them here, and we put them all together. You know, we aren't just writing down combinations as they come to us. We're thinking through each part logically. We could use a 2 and then 1 1 1, or we could start with a 1, use a 2, 1 1. Start with 2 1s, use a 2 and a 1, or have our 3 1s in front and use a 2 there. Okay. Someone said it looks like a staircase there. That's kind of intentional. Again, we're working through this logically. But anyway, how many total combinations are there? There are 8 of them. How many combinations end with a short syllable or a 1? 5 of them do. And how many combinations end with a long syllable or a 2? 3 of them do. That sequence of numbers, 8 5 3. Dun 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 dun. Are you impressed yet? No? Okay. Well, let's do the next one then. And you know, looking at this pattern, we can already kind of predict how many arrangements we should get. We got 5 for the first one, 8 for the second one. The next number in Fibonacci sequence is 13. So we're looking for 13 possible combos here. And we can start by just using all 1s, going straight across there. Okay. Now, how many ways are there using 1 2? Well, we can start with a 2 and have our 4 1s come afterward. Or we can put a 1 first and then have our 2, and then 1 1 1. 2 1s to start, and then a 2, 1 1. 3 1s, and then a 2 and a 1. Or our 4 1s coming first and then end with a 2. Again, very logical here. Okay. Then we move on to, okay, how many ways can we make a 6 with 2 2s? Well, we can put our 2 2s first and end with 2 1s. Or I could put my 2 1s first and end with 2 2s. I could have a 2 1 2 1, or a 1 2 1 2, or am I missing one? Oh yeah, of course. My 2 1s in the middle. And how many combinations do I have so far here? 1 2 3 4 5 6 7 8 9 10 11. I'm missing one combination with 2 2s and 2 1s. Do I have, oh, duh, 1 2 2 1. My 2 1s on the outside with my 2 2s in the middle. And now that I've got 12 combos, knowing I need a total of 13, my last one is going to be 3 2s here, right? 2 2 2. That's the only way to make a total of 6, you know, with 3 2s. So let me just double check. Do I have my 13 combinations? 1 2 3 4 5 6 7 8 9 10 11 12 13. There are 13 combinations. How many end with a 1? 8 of them do. How many end with a 2? 5 of them do. 1385. Right there. Okay? So, your job now is to find all the possible arrangements to total 7 using 1s and 2s. Okay? You know that you should come up with 21 total combos because that's the next number in the sequence. You'll find that this gets to get a little bit tedious as you get higher and higher, which is why, again, the essence of algebra, looking for these patterns, instead of filling in boxes to find the number of combinations and ends with a short and a long or a 1 and a 2 for a sum of 8, we can use the pattern. Instead of filling in boxes for a sum of 9, we can use the pattern. That's ultimately where we want to get to with all this algebra stuff, looking, identifying, using patterns. Okay. Now, I said earlier that Fibonacci is very much embedded in nature and art and music. You know, a composer who is writing a work in 4/4 time, those of you that are familiar with music or band or whatever, that cadence of 4, say with half notes and quarter notes, would be an example of all the different ways you could arrange them in 4/4 time. This one might be 5/4 time. This one might be 6/4 time or 3/2 time, right? Nowadays, when you can just open up a Mac computer and write a song, okay, the beauty behind it, that experience by Mozart and Bach and Tchaikovsky, you know, folks that had to sit down and compose, this is how their mind worked, whether it was directly intentional or not. You know, whether they were thinking Fibonacci when they were writing, you know, prelude in C minor, I don't know. But this is the beauty, this is the math behind it. Okay? Okay, moving on. The probability tree. This is another way to represent probability in a very organized manner. It says, the situation. Bag A contains 4 chips, numbered 1, 3, 5, and 7. Bag B contains 3 chips, numbered 2, 4, and 6. A chip is drawn at random from each bag. Calculate the probability that the sum of the 2 chips is, first task, 7, then odd, and then even. So we've used possibility diagrams in the past, and those work really well to identify the number of possible outcomes and number of successful outcomes. These work well too. And where a tree really is beneficial is when those outcomes are many, you know, not just 2 things going on, but we have, you know, 4 things in bag A, 3 things in bag B. So here's us at the start of the tree here. Okay, and we pick a number out of bag A. Let's say that we pick a 1 out of bag A. That means that out of bag B, we could pick a 2, which gives us the outcome of first a 1, then a 2. We could pick a 4, which gives us the outcome of first a 1, then a 4. Or we could pick a 6, which is the outcome of first a 1, then a 6. And as it so happens, 1, 6 is successful for our first task of finding the probability of sums of 7. But what if we don't pick a 1 in our first pick? What if we pick a 3? Well, then from bag 2, we can pick a 2, giving us the outcome of first a 3, then a 2. We could pick a 4, which is the outcome of 3, 4, which is also successful. Or we could pick a 6, which is first a 3, then a 6. What if we don't pick a 1 or a 3? Another option is to pick a 5 first. Then from bag 2, if we pick a 2, that's the outcome 5, 2, which is successful. We could pick a 4, or we could pick a 6. And again, those outcomes are listed there in the outcome column. If we don't pick a 1, 3, or 5, that means we picked a 7. And if we pick a 7, we could pick a 2 from bag 2, 7 and 2, a 4, 7 and 4, or a 6, 7 and 6, none of which are successful for our first task of getting that sum of 7. So, probability being successful outcomes divided by possible outcomes, we can see I've got 3 outcomes circled here. Those represent our 3 successful outcomes. there are 12 possible outcomes because we've got the 12 going down our outcome column here. So 3 divided by 12, that's how we get the answer 25%. If we look at all of our sums, we find that they are all odd. So our second one, the probability of an odd sum, well, they all are odd. So it's a 100% chance. And if they're all odd, that means that none of them are even, which is where a 0% chance of an even sum comes from there. Okay? So the probability tree, very nice way to organize things, identify possibilities, identify outcomes. So your task here, a bag contains a red chip, a blue chip, and a green chip. A chip is randomly chosen, put back in the bag, and a second chip is randomly chosen. Using a tree diagram, so you do need to use this, draw one out. What is the probability of choosing a red chip on either draw? So here's us. We're here. We're going to start. Okay. We reach into the first bag, and our options are either red, green, or blue. Right? Okay. Then we put that chip back. When we reach in the bag a second time, we can pick a red one for the outcome of red and red, a green one for the outcome of red and green, or a blue one for the outcome of red and blue. If we pick a green chip the first time and put it back, the second time we could pick a red chip, which is the outcome of green and red. We could pick a blue chip, which is the outcome of green and blue. Or we could pick a green chip, which is the outcome of green and green. Right? So this probability tree outlines all the different outcomes of what could happen here. Okay? And we can see which ones are successful. If we're looking for a red chip on either draw, I'm circling the successful ones there. That's what we've come up with so far. So you can finish it out here with what happens if you pick a blue chip first, what are the options for your second chip, and how many outcomes, how many are successful, etc. Okay, and finish this out. Lastly, we have our polyomino page. Each of the 10 polyominoes is used to make the large figure on the right. Your job is to identify where in that figure each polyomino is represented. They are not flipped. They are not turned. Each one is used exactly one time, and you need to identify where they are. So there you go. There's Math Packet 8. Kind of a hefty one. I think this video is pushing about half hour or so now, but it is due March 9th, and I look forward to seeing your hard work and correct answers when you turn it in. That's how you math. Don't forget to like and subscribe, and don't forget you can turn these in early for me to check over and get feedback on before they are due. So long.